Okay, thank you, and thanks also to the organizers for the invitation to speak here. Well, from a bit far now, but still. So, what I'm going to talk about today is most of what I'm going to say is joint work with Karl Liechty, who's here as moderator, and Nguyen. Some other things I'm going to mention come from other places, but most of it is based on this joint work that we're finishing now, essentially. So, okay, I'm gonna first try to start introducing the model and why I'm interested in it, and then I'm gonna try to say where I'm gonna go before I keep going with the talk. So, the basic model that I want to consider today is this model of non-intersecting Brownian motions. Okay, so it's relatively simple. I'm going to take Brownian bridges. So I have my Brownian bridges going from 0 to 0. So they start at 0, they end at 0. And I impose this condition that they are not intersecting. Okay, so essentially you just run these n non-intersecting Brownian motions. Well, you run the Brownian motions and condition them not to intersect. There's several ways to do this. One way, well, there's this sort of singular initial condition that they all start at 0 and they all end at 0. So you have to do something, but the easy way is just to make them start with some spacing, let's say epsilon apart, and then you take epsilon to 0 and you get a sensible limit. So this is it's a very, I mean, it's a model that has attracted lots of interest from combinatorics, from probability theory, and from physicists. And one of the reasons that we're interested in it is that it is essentially the same thing. I want to think about it in terms of these non-intersecting Brownian bridges, but you can think of it essentially as Dyson Brownian motion. So how does this work? Essentially, well, one way to see it is that if you look at the distribution of this set of paths at a fixed time, so this is the fixed time t that I drew here, and then you just look at the sort of the point process you get at this time, so you have a collection of endpoints. Well, those are up to some scaling, which is written there, just the eigenvalues of a GUE random matrix. I'm going to say more very briefly in the next slide what's a GUE random matrix. We have already seen some of this in the previous talk. But at time t, what you see is exactly the eigenvalues of a Gaussian complex matrix, Hermitian matrix. And actually, if you want to look at the evolution of these Brownian bridges, it actually evolves as Dyson Brownian motion, which corresponds to taking essentially the entries of the matrix, of the GUE matrix, and make them evolve as Brownian motions. And then when you see what happens with the eigenvalues, they evolve as this thing called Dyson Brownian motion, which is exactly this modulo if you want some scaling. Okay, so I'm going to talk about non-intersecting Brownian motions, but because of what I just told you, this is also a random matrix model, if you want to think about it like that. Okay. Okay, so
Daniel,
yes.
I think you might have something brushing on your microphone. I'm not sure. There was just a little bit of extra noise coming through.
Is it all the time, or when I move my? Okay.
It's kind of constant, but it's not so. I mean, I understood everything. It's just.
Okay. And
not sure
is
if
it
there's
still,
a quick fix.
Is it
I
still
don't hear it currently.
Okay, I have, yeah,
I
maybe
okay
the cable that I had connected to my tablet. I mean, if it's bad, let me know and I'll see what's going on, but I don't have anything as of now.
Okay.
Okay, thanks. So it's, for what I'm going to say later, it's worth going very briefly about the definition of these Gaussian ensembles. So I told you about GUE, which is the case of Gaussian complex matrices. I want to describe it more precisely in the case of the GOE, the Gaussian orthogonal ensemble. So what you do, this is the case of real Gaussian matrices. So what you do, and this is what showed up also in Amir's talk. But essentially what you do is you just have a symmetric matrix, and you fill it in with real Gaussians in this way. So you have to choose some normalization. This is the normalization that I chose. Okay. And then the random variable that's going to play a role in the story I'm going to tell is the asymptotic fluctuations of the largest eigenvalue of this GUE random matrix. So this is what's called or usually known as the Tracy-Widom GOE distribution. So what it turns out is that if you look, so this one here is the largest eigenvalue of my random matrix. And that one with the scaling turns out to be around this edge, which is at 2 root n. And the fluctuations are of this size, n to the 1/6. Sorry, the fluctuations are of order n to the minus 1/6. So it's pretty tightly located around this edge 2 root n. And if you scale by this amount, n to the 1/6, then you have convergence to a non-trivial random variable. This is what's called the Tracy-Widom GOE random variable. So it's the asymptotic fluctuations of the largest eigenvalue of such a matrix. Okay, and even though, I mean, here it's not necessary to say it, but we will see these things come up later. So let me tell you one way of expressing this distribution. So if I look at this probability distribution, the probability that this random variable is less than r, then it's given as what's called a Fredholm determinant. So most of you, or many of you at least, will have seen what's a Fredholm determinant. But essentially, what I get is the determinant of an infinite dimensional operator. So it's this operator, in this case, BR, I call it BR, and it's nothing but Airy of x plus y. So you should think of this as a sort of as a matrix, but indexed by positive reals. There's a typo here. It should be x plus y plus 2r in this case, like what's being shown there, but this is not very important. And you're computing the determinant of this sort of infinite matrix, if you want. So really, it's an operator from acting in L2 of 0 infinity. And there's a way to make it precise, and it's exactly the right generalization of finite dimensional matrices. But there's another way, which is equivalent, or this is one of the ways to do it, which is just to compute the sum that's written here on the right. So essentially, you have to take this kernel, compute certain finite dimensional determinants, put them together a certain way, and sum, and you get the formula. Okay, but most of what I want to say is that these distributions, distributions such as this one and other ones we will see, are naturally given for reasons that I probably won't have time to get into, but we'll see a little bit of that. They're naturally given as Fredholm determinants. So as determinants of certain kernels, and what you have to do is try to say what's the kernel. Okay. Okay, so this is the Tracy-Widom GOE distribution, and so there's going to be some index here. It's going to show up in some places of the talk. So this is the usual beta equals 1 case, and this is because we're taking real random variables. And then there's also a case of beta equals 2 and beta equals 4, which corresponds to complex and quaternion random variables, still Gaussian. And in that case, that's the GUE and the GSE. So it's a very similar story. So for instance, for GUE, what you have is you have complex Hermitian matrices filled in with Gaussians, where the real part and the imaginary part are independent. Okay, so these are the Gaussian ensembles, and I'm interested in this type of random variable. Okay, so as I was saying, maybe just to go back very briefly, this point process that one sees here, that's exactly the eigenvalues of the GUE random matrix. Now, there's the following thing one can do. So in this sort of problem, one is often interested in trying to compute the statistics of this top path. Okay, so it turns out that if you focus on the top path under this scaling, so again, the scaling here is sort of the same random matrix scaling, and I have to zoom in at this scale into the 1/3 here at the top. So I'm looking at some sort of little window over here, and I zoom in. Then what I get, and this is a classic result by now, is that this top path of the non-intersecting Brownian motions, or this top path of the dice of Brownian motion, if you want, converges to something called the Airy 2 process. And it's really not the Airy 2 process. You have an extra parabola, so the curvature is parabolic, so you see this parabola in the limit, and on top of that parabola, you have this Airy 2 process. And, well, okay, one thing maybe before that is that the Airy process, this Airy 2 process here, is a stationary process, so it's going to look, okay, it's not a very good picture, but it's going to look sort of, it's a really bad picture, but it's going to look sort of stationary. It looks locally like a Brownian motion, But the point is that the marginals, so if you look at the 1-point marginals, those are what I would be calling the GOE Tracy-Widom random variable. Simply because, remember, this is the top eigenvalue of a finite random matrix. Okay, so in the limit and with the right scaling, and this is the right scaling, what I get is something that's exactly Tracy-Widom GOE, but it's sort of a dynamic version of that. Okay, and there's an old result which was shown by Johansson, and it comes from something completely different. It comes from KPZ, and I'm going to get to that later. That tells you that if you compute the soup of the Airy 2 process minus the parabola, so you sort of, after you take the limit, you compute this soup, then what you get is exactly, well, modulo this prefactor, this 2 to the 1/3, but what you get is this Tracy-Widom GOE random variable. So you start with this sort of this dynamic version of GUE, or the, if you want, the scaling limit of the Dyson-Brownian motion, but for the GUE, and when you compute the soup of that, what you get is this Tracy-Widom GOE random variable. Okay, so this is not really a random matrix fact. This is really, in a very particular sense and a very concrete sense, this is a KPZ fact. I'm going to get to KPZ later, but I mean, it's sort of important to keep that in mind. But for now, what I want to say is that, okay, so on the one hand, we know that this top line converges to the Airy process. And on the other hand, we know that the soup of the Airy process is GOE. So essentially what this is telling us is that if I look at the maximal height, so this maximal height here, if I look at the maximal height of my system of non-intersecting paths, and if I rescale this correctly, I may be, probably I missed a 2 over there. But if I rescale the maximum of this system of non-intersecting Brownian motions, then that correctly scaled converges again to a Tracy-Widom GOE distribution. Okay, so this essentially follows from what I just told you. You have to sort of prove a good sense of convergence for these convergence to the Airy 2 process. So that was provided by a paper of Ivan Corwin and Alan Hammond. That's also going to work for us later in the next process that we're going to see. But again, so you're looking at GUE objects, you look at the soup, and you get convergence to these Tracy-Widom GOE random variable. Okay, so this is sort of the starting point. And what there's yeah, I wrote it. So there's by now several proofs of this fact. There's really sort of different ways to look at it. There's things that people in combinatorics have done. There's several proofs from the community of people working in KPZ and random matrices, and also from physicists who were very interested in this for quite a while. Okay, so what I want to talk about today is the following problem. I'm going to try to explain why some things which I would say are sort of interesting, or some interesting things will happen, is what happens if now, instead of having all the Brownian bridges go from 0 to 0, I take m of them, the top m, so in this picture m equals 2, and I let them go from arbitrary locations, okay, which here I call alpha and beta, okay? So again, there's in this case 2 paths, and they don't go from 0 to 0, they sort of join arbitrary locations. So you're going to get a picture like this. And of course, okay, I have to say what the scaling is going to be, because I'm going to be interested in taking n to infinity. And my question is, what happens with the soup of the top path? Okay. So, well, I knew from essentially all this picture here that this top path, this height is around root 2n. Okay. So it makes sense to scale these endpoints around root 2n. Okay, and with the same scaling that we saw before. So essentially what I'm gonna do is we're gonna let these endpoints be around root 2n and fluctuate sort of in this scale of n to the 1/6. Okay, so that's what we do. We do that for alpha, we do it for beta. And well, there's going to be some ordering, which just means that the top path is the one with label 1 because of this minus sign. But there's an additional condition that we have to impose for what I'm going to say next, which is that it's this geometrical condition over here, which essentially it's there just to make sure that, okay. So suppose I did something like this. Suppose the top path was over here. If the top path is too high, I mean, sort of in the limit, it will never interact with the bulk of the other Brownian motions. So to see something interesting, I want the top path or the top paths to really sort of push into the bulk of the main part of the system. And with this scaling, it turns out that this is exactly this minus A1 less than B1 is exactly the right thing to do. Okay, it's just a geometrical condition, which means that essentially the path joining these 2 points sort of enters below the top of this ellipse. Okay, but it's just a condition that one has to impose. And okay, there's again a result by Adler, Ferrari, and Barmorbici, who studied exactly this model, and they did exactly the same scaling as before. So they look at the top path, and they ask, well, what happens in the limit? And what they get is, again, convergence to something, a sort of Airy process. They called it the Airy process with wanderers. So these top paths are the wanderers. And again, minus upper hour. Okay, so that's the result by them. And then I should say, so here's another connection with random matrices. So remember again, one more time, that if I look, say, at a fixed time, then what I'm seeing is the eigenvalues of GOE random matrix. Well, here it's sort of the same in a special case. So if I let, one thing I should say is that there's no problem. So let me go back just a moment. There's no problem letting these, let's say these ones or the right ones. It makes complete sense to, not the A, sorry, these A's here. It makes complete sense to let those be infinity. And if you look at the scaling that I chose here, if I choose all the A's to be infinity, all that I'm doing is pushing all these alphas back to 0. Okay, so in that case, what I have is, so I'll do a picture here. What I have is something where my path is starting over there and going to, I don't know, some position over here. Okay, and when I do that, the top the eigenvalues, when I look at them sort of from the point of view of the edge, those are exactly something called the Tracy-Widom, the spiked Tracy-Widom distribution. Or really, if you look at before taking the limit, if you look at the point process that you see here, it's again the eigenvalues of a GOE matrix, except that now this GOE matrix has been spiked. So you have sort of moved, you have added a perturbation which moves the first M eigenvalues. Okay, I'm gonna also say that about that later. Okay, so that works at least when these guys are infinity. It's not clear what's the relation in the general case. And for people who are more familiar with these things, this Airy process with wanderers, it also shows up in last passage percolation problems where you add some boundary sources. Okay, that's where it comes from in the KPZ world. Okay, but anyway, we have this convergence, and we have a complete description of who's this process. It's a perturbation, if you want, of the Airy 2 process that showed up in the case without the outliers. So what I'm going to be interested in is in studying exactly just like before, that we were studying the soup of the Airy 2 process minus a parabola. Now I want to study the soup of the Airy process with wanderers minus a parabola. Okay, and that's the asymptotic maximal height of this system of non-intersecting Brownian motions without outliers. So essentially, again, I'm looking at the top path, and I'm asking what's the maximal height after I take a limit. Okay, it's also point to line last passage. It's also the point to line last passage time for this last passage percolation model. But again, I'm not going to get into that. So this is the main object that I want to study, and I give it this name. Okay, so it's the asymptotic maximal height. Okay, so a couple of things one can say right away. I mean, things one should at least expect directly. So one can wonder what happens if I take sort of the normal, the usual, not the usual, the natural limit transitions. So the first thing that I can wonder is what happens if I take all the parameters go to infinity. And remember that when I do all, when I let all my parameters go to infinity, that corresponds to letting the endpoints really start at 0. Okay. So as I do that, I mean, these are, there's an interchange of limits here, but I first take n to infinity, but then I let my a parameters and my b parameters go to infinity. And so I should recover what I got when everybody started at 0. So this is the first thing one can say. Well, as these a's and b's go to infinity, I should recover my Tracy-Widom GOE distribution. Now, there's another thing one can do. So I'm going to think of all the a's and all the b's as being positive. And remember that they are being, so if you want beta I equals root 2n minus n, oops, I guess you can't see that, but it's root 2n minus n to the 1/6 bi. Okay, so I'm going to think of all the b's as being positive, all the a's are being positive, so everybody's starting below this line. But what happens is that as all these a's and b's go to 0, I am now taking, erase these ones, I am now taking everybody and making them go up. Okay, it's as if my outliers started over here. And you can sort of convince yourself that in this case, the fluctuations are completely different, because the top path is starting at the sort of at the predicted maximal location, and the maximum is not going to happen near the center, but the maximum is really going to happen near the edge, and it's going to be sort of order 1, because the path is going to sort of wander around here and then, well, keep going. So at least the maximum is going to happen. I mean, you have a bound. The maximum is at least going to be whatever happens when you depart, and essentially that makes the fluctuations go to infinity at this scale. So as b goes to as all these endpoints go up, this is not the right scaling, and this random variable goes to infinity. So okay, I say that's what one should expect. Okay, so the first thing that I want to now show as a result is a Fredholm determinant formula for this maximal height. So very briefly, I essentially won't say anything about proofs, but one can write using some known results. One can write a formula, a completely explicit formula in terms of a Fredholm determinant for the probability that, so because I want to compute, remember, I want to compute the sup of the Airy process minus a parabola. So really what I would like to do is to compute the probability that the Airy process is below some function, and then I'm going to let the function be constant. So there's a general formula which involves a Fredholm determinant, and this Fredholm determinant, it involves some kernel, and the nice thing is that the kernel is defined in terms of a Brownian motion, the probability that a Brownian motion hits my target function. Okay, so I have my function over here, and I want to know what's the probability for the Airy process with wanderers doing something, and really you end up having to compute the probability that a Brownian motion hits this function, okay, between minus L and L. And then you're going to take L to infinity to recover the probability on the whole line. This is very general. Actually, this turns out to be a general result that can be applied in many situations, and it works in this case. And the nice thing is that for the problem we're interested in, G is just a line, right? Because I want to replace G by R. So I'm really asking the probability that a Brownian motion hits a straight line, and that I can compute explicitly by the reflection principle. So everything is explicit, and you can compute, and you get a formula, okay? And the formula is that, well, the distribution of this random variable that I'm interested in, of this maximal height, is the Fredholm determinant of a certain kernel, and the kernel is it's written explicitly here. Okay, so it's an explicit form. One thing to note is that when all the AIs and BIs go to infinity, essentially this product here is completely gone, and I'm just left with the blue part, this one. And that's exactly you won't remember probably, but it really corresponds precisely to the kernel for the Fredholm determinant that gave you the Tracy-Widom distribution. So from here, one can see already that you do recover the prediction that as all the A's and B's go to infinity, you get Tracy-Widom GOE. Now you also get something else, which is, to me, it's still surprising. So you can see that the A's and the B's here play a completely symmetric role. So this means, maybe you can draw a picture, but it means the following. Well, it means that this distribution equality that I wrote here, it means that if I look at paths, okay, I have my non-intersecting Brownian motions, and if I do the following thing, if I do, say, two paths going from here to here, one path. So if I look at the max of this system, that's the same in distribution, exactly the same as if I computed the same thing now with two outliers. They both start from 0, but one ends here and the other one ends, well, it's not the right picture, sorry, but so one ends at one height and the other one ends at the other height. This is not correctly written. So these two heights should correspond to this height and that height. Okay, but I guess you can see it. Why would that have to be the case? I mean, we don't know. But it just follows from the formula that there's this symmetry between having, if you want, say, one outlier or two outliers when you sort of tilt things in this way. Okay, so this is one consequence of this formula. And an important consequence is that for the rest of the talk, I'm going to always take the starting points to be sort of 0 or infinity in this notation. Okay, so this is, if you want, this is the starting point of the rest of the. Now, in a sense, I'm going to give you some sequence of consequences and relations with other objects which come from this formula. Okay, so the first one is essentially integrability for this quantity. So for that, I'm going to go back a little bit to the Tracy-Widom distributions. So here's a very famous result by Tracy and Widom. And it tells you that the GOE distribution, the Tracy-Widom GOE distribution, again, these asymptotic fluctuations of the top eigenvalue for this random matrix, they can be expressed through a very basic object in integral systems, which is the Hastings-MacLeod solution of the Painlevé 2 equation. So what you have is, you have this simple ODE, Q double prime equals RQ plus 2Q cubed. And you choose the solution which looks asymptotically like the Airy function. So the same Airy function that showed up in the kernel for the GOE distribution. The one that behaves asymptotically like the Airy function as x goes to infinity. So that's called the Hastings-MacLeod solution to the Painlevé 2 equation. And now it turns out that you can write, as I was saying, the GOE distribution, this Tracy-Widom GOE distribution, as e to some integral of q. But it's essentially, it's determined by q. There's a simple expression which gives you that the GOE distribution, well, equals these quantity in terms of q. There's also similar ones for GRE and for GSE, so for the complex and the quaternion case, but we won't need them. Okay, so this is, I mean, this is really the source of lots and lots of work, of subsequent work, and there's many relations between random matrices and sort of Painlevé systems. Not only Painlevé 2, there's others in some other situations, but it's something that has really sparked lots and lots of interest in many senses. So well, one can wonder if one can say something about Painlevé 2 in this context, in the context of the process of the random variable that I'm discussing. And the answer is yes, but it's not going to be exactly in terms of Q. It's going to be in terms of a couple of functions that can be defined in terms of Q. So what you have to do is you have to, okay, let's maybe focus on this one. So you have to solve this PDE, not this PDE, this ODE, okay? So I'm going to, there's two functions, f of x and w and g of x and w, and you solve this equation with this initial data. And it turns out that if you do this, you're also solving this equation. Okay, this won't be too important for what I'm telling, but it's essentially the solution of an ODE where it's a linear ODE, but the coefficients are exactly this Hastings-Vac-Lowd solution for Painlevé 2. Okay. So you define these functions. It's again functions defined in terms of Q, and you have this property. This is called a Lax pair for the Painlevé 2. That just means that these two equations are compatible because this is sort of overdetermined, but they end up being compatible, and that's equivalent to this equation here. But anyway, you define f, you define g, and here's the result. So the result is that. So again, I'm restricting to the case where everybody starts on the origin because it makes no difference due to the symmetry. And well, you can express, so let's maybe look at the one for the case of m equals 1. So this one. So this distribution is exactly the Tracy-Widom distribution multiplied by a combination of f and g. There's some scaling factors of powers of 2 to the third. Okay, and in the general case, you get something like that, but it involves a certain determinant. So yeah, you can also do it in terms of Painlevé 2 in this case. A formula such as this is not, I mean, it looks surprising. It's, in a sense, it's not so surprising. It's similar to a formula that Jinho-Baek proved for what I mentioned, the spiked Tracy-Widom distributions in the case of GUE. But it can also be, I mean, it also shows up here. One nice thing is that these functions f and g are well understood. And if you take limits, you recover exactly this behavior that I told you about at the beginning, that as b goes to infinity, you get the Tracy-Widom GOE, and as b goes to 0, you get infinity. It follows from the behavior of f and g. And well, we have sort of two proofs, but essentially it follows from the Fredholm determinant formula. So from the Fredholm determinant formula that I showed you, one can sort of manipulate it for a while and get to this formulation from knowing things about f and g. Okay. So now a separate relation. So what I've been mentioning a couple of times. So let me very briefly introduce these spiked Tracy-Widom distributions. So the spiked Tracy-Widom distributions are the asymptotic fluctuations of eigenvalues in the random matrices which have some perturbation. Okay, so one way to think about it is, let's say you take GOE and you add a finite rank matrix scaled in a certain way. Okay, so as you add a finite rank, let's say a rank 1 matrix, you are sort of moving. If you scale things correctly, you are moving the top eigenvalue. So now the top eigenvalue is not gonna, if you don't perturb too much, the new eigenvalue is sort of gonna fall in the bulk, and the top eigenvalue of your matrix is gonna still look the same. But if you do it just right, then you're gonna see something interesting, and the top eigenvalue is gonna do something slightly different. Okay, so you can do that in more than one way. You can do it in the way that I just described by adding a perturbation, and this is something that people are interested in too in statistics, because you can take Wishart matrices, which are covariance matrices of random Gaussian population, Gaussian samples, and if you sort of take the covariance matrix to be spiked in this sense, then you get again not convergence to the Tracy-Widom distributions, but to these spiked Tracy-Widom distributions. Okay? and there was an open, they satisfy something similar to what I just showed you. Okay, I'm going to skip this in the interest of time, but what I was describing here is that there's lots of similar connections between spiked Tracy-Widom distributions and everything that I have been talking about. Okay, so it's natural to wonder whether this top eigenvalue could have to do with the spiked Tracy-Widom distribution. Remember that I told you that this Airy process with wanderers really is the top. I mean, if you look at one point, it's the top eigenvalue of the spiked Tracy-Widom distribution. Okay, so maybe one can wonder, okay, what happens with the object we are looking at? Okay, and here's the result. So again, it's not quite that. There's not a direct relation, but here's a relation we found. Okay, so there was an open question about how to describe the spiked Tracy-Widom distribution. So again, so I'm going to state it only in the case of one spike. So instead of having an m parameter family, I'm going to have a one parameter family. So I do a rank one perturbation. Okay, and there's a very nice result by Bloemendal and Virág, who showed that if I do, again, one spike for general beta, so beta here could be beta equals 1, 2, 4, or actually anything larger than 1, because there's a generalization, then the distribution of this top spiked eigenvalue satisfies this PDE. It's the unique solution to this PDE with this boundary behavior. Okay, they show other things as well, but this is one of the results they have. Okay, it's a very nice, it's a universal, if you want, description of this distribution. It works for every beta, and beta only shows up here as sort of part of one of the constants in front of this PDE. So what we found is the following thing. We found that in this case, our distribution, and I'm again stating it only for the case of one outlier, our distribution is the unique solution of the same PDE. It's exactly the same PDE. The boundary condition is sort of, okay, in infinity is exactly the same, but this boundary condition of W going to minus infinity, which I didn't describe, it's changed to B going to 0. So as B goes to 0, you get 0. In the old version, it goes as W went to minus infinity. But what's weird, up to a point, is that the beta value that you have to do there is beta equals 4. So somehow, this distribution, which is converging to the GOE, the Tracy-Widom GOE distribution as B goes to infinity, it comes from this Bloemendal-Virag PDE, from a version of this Bloemendal-Virag PDE for the spike Tracy-Widom distributions, but for beta equals 4. And again, we don't really have a good explanation for that. It may not mean anything, or it may mean that there's some relation between the beta equals 1 and beta equals 4 cases. Such things are known in random matrices. There are dualities between the GOE and the GSE cases. But for now, well, this is what we found. So somehow, the other thing that's nice about this is that it gives some idea about that this Bloemendal-Virag PDE shows up more generally in not only for spike Tracy-Widom distributions, but in a more general setting. Okay, I see that I'm sort of starting to run out of time, so I'm going to very briefly. I hope to get to this with more time, but anyway. So I want to describe very briefly the connection, the other connection, which is with KPZ fluctuations. So I won't have time to describe these very in much detail, but the idea is the following. So now I have to describe what's the KPZ fixed type, okay? And one way to think about it is the following. So now I have a growth process, okay? This is the standard Tay-set model, where you have particles jumping to the right at rate 1, but they can't jump on top of occupied sites. So a jump like that is forbidden, okay? And on top of that, you can draw a height function where you have this, essentially above every particle, I draw a line of slope 1. Above every hole, I have a line of slope -1. And now the dynamics is that a corner such as this is going down to that at rate 1. Okay, so this is a simple evolution process for a height function, and this is one of the most basic models in the KPZ universality class. Okay, so the prediction, the big prediction in the KPZ universality class, or one of the predictions, is that the fluctuations of this interface should be, so the interface is going to go down in the way I described. It's going to go down at a linear speed, but then the fluctuations, it should fluctuate around this sort of predicted position at a scale of t to the 1/3. So this is the famous t to the 1/3 scale in KPZ. And then the correlations should occur at a scale of t to the 2/3. And so, okay, one can turn this scaling into a scaling like this. So now I fix t, but I have a new parameter where the 1, the 2, and the 3 are showing up. But let me go quickly. And in a completely separate work with Konstantin Matetsky and Jeremy Postel, we showed that, so maybe, since I don't have too much time, this is a better way to describe it, maybe. So consider now this TASEP with this particular initial condition, this narrow wedge initial condition. So I start like this, oops. I start like this and I run it down. So after a long time, I'm going to see a path, which is, again, the Airy 2 process minus a parabola. It's exactly the same process that I mentioned for non-intersecting Brownian motions. Okay, and this corresponds to. Okay, let me stop it there. Let me now say what happens if you start with a flat interface. So now I start with an interface which looks like this, and I run it down. Well, what I see is something called the Airy 1 process, which corresponds to Tracy-Widom GOE fluctuations. Okay. So this was known, and this was known from essentially the 2000s, and it worked for these special initial conditions. So the two that I showed you and a couple more. And what we showed a couple of years ago with Konstantin and Jeremy is that actually this works in general. So if you take TASEP, and as long as the initial condition converges in the right sense to some general profile, then the whole system converges to something we call the KPZ fixed point, and it's a Markov process evolving in time. Okay, and the idea is that this should be the scaling limit of all models in the KPZ class. So every model should be described by this limiting object, which we constructed out of TASEP, basically because we have explicit formulas in that case. So it should be the scaling limit of all models, and it's known now for a couple of them, but universality is an open problem. So here's the result we got with Karl and Bao. It is the following. So you should, maybe I should just stop one moment to say that you have a TASEP initial condition, and that converges in the diffusive scaling to some limiting profile. And now you describe these Airy processes as the KPZ fixed point started at that profile, okay, after you took the limit. And this profile is what I call the H0. So it turns out that our system, our random variable, this top height of the Airy process with wanders, is in distribution equal to the KPZ fixed point, or if you want, to the asymptotic fluctuations of the height function of TASEP, with a specific initial condition. And the initial condition is the following. So for m equals 1, if I just do one path, then it's simply a reflected Brownian motion with a downwards drift, and the drift is of drift b. So b is this parameter that so you run it, and it's reflected at the origin, but it has this downwards drift with this drift going down. That has a stationary measure, which is exponential. And then you have a stationary version of this process. Now you have a stationary reflected Brownian motion. Well, it turns out that if you start the KPZ fixed point with this reflected Brownian motion, this stationary reflected Brownian motion, then you get exactly the distribution that we're interested in. And if you want to get more, a larger M, what you have to do is you first run what I just told you, Then you run another reflected Brownian motion, but now it's reflected on the first path, and you keep going. So every path is reflected on the bottom one, and you keep going, and you do it m times, and you get to say this path, and that's going to be the initial condition for the KPZ fixed point. And for that initial condition, that's exactly the same thing as this random variable. Okay, I'm going to stop. I didn't have time to say the last thing, but as a direct consequence of this, we get that, as a direct consequence of this and earlier work, we get that these top, again, if I look at this probability distribution, the one of this maximal eigenvalue, not eigenvalue, the maximal height of these non-intersecting Brownian motions with outliers, if I scale things correctly, then this function, or rather the second logarithmic derivative of this function, solves another famous equation, or a more famous equation, the KTD equation. Okay, so this follows from work that we did with Jeremy Postel, which holds in great generality, but this is a new example. So here, now we know that also for the KPZ fixed point with this reflected Brownian motion with downwards drift in the stationary version, that satisfies the KDD equation. Okay, so we have all these connections, and it sort of shows that these PDEs and the spike Tracy-Widom distributions play a role both in the random matrix side and in the KPZ side, and it's sort of one more example of this connection between the two subjects. Okay, thanks.